All right. So as mentioned last time, when we were talking about finite element methods and some of the different element types that are available to you, I talked about really three different categories broadly of elements that might exist in some finite element code. There's certainly solid elements. Those are three-dimensional volume-filling elements like tetrahedra and hexahedra, and they're intended to discretize some three-dimensional volumetric domain. And that worked really well if the domain that you were interested in was truly, a nice bulky three-dimensional domain like a continuum potato or any other kind of thing that we've looked at previously. But if the geometry of the structure you're looking at is maybe not so three-dimensional, maybe it's closer to, a long, slender structural member, or maybe it's a flat plate or something like that. In those situations, if you tried to use these three-dimensional volume-filling elements or solid elements to discretize those structures, then you'd need a heck of a lot of them in order to be able to get a good quality mesh where all the elements have a nice aspect ratio. But there were other alternatives that you could employ, other types of what I called structural elements, things like beams and plates, things that have a relatively long dimension, maybe or two long in-plane dimensions and one or two other relatively thin dimensions. So beams are certainly something you've probably had a lot of exposure to in your previous coursework. So I'm sure you probably already have a good sense of exactly what goes on behind the scenes in representing structural members through these one-dimensional beam idealizations. Plates, however, are probably something that you've maybe heard about, and certainly you interact with them on a day-to-day basis, but in terms of how that connects to the theory of both the theory of elasticity and classical beam theory, as you might be familiar with, how those things connect together is anything but clear. So really today's lecture is intended to unify some of your thinking about the theory of elasticity, as we've discussed up to this point, which is a fully three-dimensional theory of how do structures deform under applied loads, considering all different forms of strain in this three-dimensional sense and stress in this three-dimensional sense. And we're going to take that theory and try to simplify it and relate it back to classical engineering beam theories. And at the same time, just for fun, as kind of an extra add-on, we'll talk about plate theory. And how does that also relate to this idea of simplifying the theory of elasticity such that we can come up with these, relatively simple idealizations of what's going on with the kinematics or the deformation that is assumed in how these different structures deform. So, like I said, we're going to go through this and answer a few critical questions of interest. Again, we want to know how exactly does everything that we learned up to this point relate back to all of the previous coursework that you might have had in structural analysis and strength of materials and statics and all those things where you were usually looking at trusses or beams, these one-dimensional structural members, and you did all of your analysis in that context. The theory of elasticity really expanded the perspective. Now, things were three-dimensional, but it certainly made finding solutions to these fully three-dimensional problems rather complicated. So we do still like to, apply classical beam theory in situations where, we can apply it reasonably, but we need to know when exactly is it applicable to go back to using various forms of beam theory or plate theory if you're trying to idealize how does a plate deform under some kind of transverse loading and bending. So we want to know, when is beam theory, classical beam theory, still relevant, and when can we use it? And what are the things that we sacrifice when we go from this fully three-dimensional, very general description of structures and how they deform under loads down to these structural representations? So what are the simplifications being made, and what do we lose? So all these questions are things that hopefully we'll get to and we'll try to answer. And I want to point out that this is sort of I'm pulling a lot of different information from several of the chapters that exist in the textbook. So there's chapter 5, which is nominally on beam bending. Chapter 13 is plate bending. So we're kind of doing both of those at the same time to get you a unified perspective on the two, because they are very much related to each other and very similar in many ways. And then chapter 6 talks about torsion. So really all these things are simplifications of the kinematics and the description of three-dimensional domains into structural domains. Okay, so let's begin. Let's actually start by revisiting a problem that we discussed, well, maybe over a month ago at this point, back in chapter 3. You might recall this problem. We were looking at a cantilever beam, which really was a thin plate that had some finite thickness T, but that dimension T was relatively small compared to the overall depth of the beam, measured as 2h, and the overall length of this beam, which not shown here, is some length L. We went through a lengthy derivation to come up with the solution to this plane stress elasticity problem, enforced all the boundary conditions. We used Airy's stress function to come up with the analytical solution as shown here for the in-plane displacement fields, displacement in the X and Y directions. And from that, we could also figure out what are the resulting strain fields, the epsilon XX, epsilon YY, and epsilon XY shear strains, how they varied as a function of position within this, plate domain, as basically plane strains, assuming that the out-of-plane strains, or in other words, the transverse shear strains, or the normal strain, normal to this plane, we kind of said, well, we don't really care so much about those details. We're just treating it as a plane strain problem and a corresponding plane stress situation. So we have all the different in-plane components of strain, stress, and displacement. And we looked at all these different interesting features of the solution. And we said, this doesn't look exactly like what I think it should look like based on the assumptions of beam theory, what you might be previously familiar with. Now, I want to recall that there were a few features that were distinguishing about this particular problem. And in particular, shout it out if you remember. What are the primary kinematic assumptions of classical beam theory, sometimes also called Euler-Bernoulli beam theory?
Displacement should be continuous.
Displacement should be continuous. That's kind of a general rule of thumb. We need to have compatible solutions. But in terms of, I'm specifically looking at what were some of the assumptions in Euler-Bernoulli beam theory, and how did they relate to assumed forms of deformation that take place on individual cross sections of this beam? Plane sections remain plane. Yes, exactly. And there was maybe another one, at least particular to Euler-Bernoulli beam theory. Besides, say again? Homogeneous materials? Well, that's also an assumption, but tangentially related, not necessarily directly an assumption of beam theory. Anyone's guess? Well, I'll give you a hint. It had something to do with how this plane section, if we assume it remains plane after deformation, we also made an assumption about what its orientation was relative to the neutral axis of the beam. What was that assumption? Yeah, it has to remain not just planar, but also perpendicular to this neutral axis or neutral fiber in the beam. So clearly, those two assumptions, plane sections remain planar and perpendicular to the centroidal axis of this deformed beam, appear to be violated. First of all, clearly this section is not planar, at least according to this elasticity solution that we derived. It has this funky kind of S or curved shape. So clearly that assumption is a simplification that beam theory just kind of says, well, that's good enough. Let's just assume that it's roughly planar. But in general, that's not true. In general, real solid materials, in terms of how you discretize them, will not remain perfectly planar. They might start to warp or kind of basically deform in a way that is inherently non-planar. So if we introduce this general theory of elasticity, the solution is telling us that fundamentally the assumptions of beam theory are wrong. It's not that it's like, that was something that maybe you felt like is just a truth, an inherent truth of how things behave, but really it's just not true. As we'll see, all models are wrong, but some of them are actually quite useful, which is why we'll rationalize exactly when is this model still applicable and useful. But nonetheless, we don't have plane sections remaining planar, and even worse, we don't even have that the plane section remains perpendicular to the neutral axis. If you consider some maybe small square of material that was maybe located next to this section, close to the neutral axis, you'll notice that it actually undergoes a little bit of shear deformation, which implies that indeed this plane section is actually not perpendicular to the deformed neutral axis of the beam. So on both counts, we don't satisfy these conditions of classical beam theory. However, we can still do some interesting investigations and examine what happens if we were to maybe shrink this tangential dimension or this depth dimension h such that it becomes smaller and smaller. So the slenderness of this beam, as it begins to increase, we notice some interesting things. There's a bunch of terms that appear in the solution for all these different displacement components and strain components and even the stress components, which depend on, spatial position and some of these different, geometric parameters defining this beam. So clearly, any terms that depend on h, as h becomes really, really small, those terms that depend on h are also going to become smaller and smaller, especially if they depend on things like not just h, but maybe h squared. So as those, as you shrink the dimension of this beam smaller and smaller, you can safely neglect those terms or reasonably neglect their influence. And additionally, any terms that depend on, let's say, y squared, where y varies between plus or minus h. Again, the largest value that these terms that depend on y squared can attain are proportional to h squared. So those two can be safely neglected or ignored. And if you go through and you examine what are those terms that we can neglect or cancel out, at least in this simplified solution, we notice that a lot of things go away. Some of the terms that previously accounted for this plane section remain basically being non-planar in terms of how it deforms into this funky S-shaped curve. This term goes away. And what's more interesting also is that the representation of the shear strain, which depends on a term involving y squared and h squared, both of those y squared, h squared terms we can safely neglect, which basically implies that we can reasonably approximate that the shear strain is close to zero. It's not exactly zero, nor is the shear stress zero. It'll vary actually through the depth of the beam, and we know this. It'll vary kind of like a parabolic distribution. But ultimately, at the end of the day, we find that we have a description of the deformation in the limit as the depth of the beam becomes smaller and smaller, which basically says that even though we know that Euler-Bernoulli beam theory, it's not quite right, it actually does a pretty darn good job for relatively slender beams. And that's the main takeaway from this examination, is that even though this is somewhat of a limited example, it's just one particular elasticity solution, it's nonetheless worth noting that the takeaways from this analysis of what happens in the limit as you start to basically increase the slenderness of this beam or decrease its depth, that the same thing will happen regardless of what the cross-section of the beam is or other kinds of details like that. So it becomes applicable as you kind of decrease the depth dimension of this beam. And we recover some of these assumptions of beam theory, saying that the shear strain is roughly negligible or close to zero is kind of equivalent to saying that this little square of material won't undergo any kind of shear deformations, which is to say that these edges of this square after deformation will remain roughly perpendicular to each other, which is essentially equivalent to saying that this plane section will remain perpendicular to the deformed neutral axis of the beam. So we recover this, classical assumption of plane sections remaining perpendicular, and also we have the funky S-shaped contribution to the planar deformation of this section. That term goes away, so we just have a term that's basically linear in y, which is equivalent to saying that the deformation really can be idealized almost like a rigid rotation almost of one of these sections. So we recover these assumptions of beam theory as a special case of our more general theory of elasticity. We can derive everything from that perspective, and we can apply it not just to beams, but we can apply it to other types of structural members as well, like plates. So as I said, a beam is really just one long structural member that has one characteristically long dimension and two characteristically shorter dimensions. We'll call them the transverse direction, where there's this long dimension we'll call the axial dimension. A plate is kind of analogous in the sense that rather than having one long in-plane dimension, it has two long in-plane dimensions and one characteristically short or thin dimension. So we'll still call this the transverse direction, but we'll call X and Y the in-plane dimensions of the plate. So in some sense, beams and plates both involve this limiting process of looking at what happens to the elasticity solutions that we might derive for some general structure. What happens as we shrink these transverse dimensions to be smaller and smaller, increasing the slenderness of the beam, or basically shrinking this thickness dimension of the plate down to zero. In both of those cases, we get a simplification of what happens kinematically to individual chunks of material that we might look at, either by cutting through this beam and looking at a particular cross-section and how it deforms, or cutting out maybe a small fiber or kind of chunk of material from the middle of this plate and looking at how does it deform under various loading conditions. So in both cases, we can apply various simplifications, and we can develop beam theories and plate theories generally, which attempt to represent those simplified kinematic assumptions in a nice pithy way that we can maybe characterize through some interesting relationships. So in terms of how these different structures deform, particularly under transverse loading, I'm just going to isolate attention, at least for the time being, to looking at what happens to these different structures when you apply loading in a direction that is strictly transverse to the longer dimensions, either of this beam or of this plate. So if I apply maybe some in-plane or transverse loading to this beam, it'll deflect transversely. And it might deflect in the Y direction, or it might deflect in the Z direction, or it might deflect in some kind of combination of the two. So under transverse loads, I obtain these kind of transverse displacements of my beam. In comparison, plates are a little bit different. There's only one transverse direction for this plate, and consequently, there's only one transverse direction that I'm going to consider applying loads to, and that's the Z direction. So if I'm trying to apply transverse loading to this plate to cause it to bend or warp in an interesting way, all I have to do is apply basically pressure loading on the surface of this plate. Whereas in the case of a beam, I have to apply some kind of distributed line load that acts transverse to the axial dimension of this beam. So in both cases, they undergo bending processes. But exactly how you interpret bending looks different if you're looking at a beam as compared to a plate. So a beam, can bend at least in any out-of-plane dimension, whereas bending has this much more interesting representation when you're considering deformations of this surface almost. And we'll dive into the kinematics of how that's exactly represented a little bit later. But to really set ourselves up for success, we really need to establish more rigorously what exactly is this, beam theory or plate theory that we should be using, and what exactly are these assumptions. Well, we already know beam theory, and we've already established what are the fundamental assumptions, kinematic assumptions of beam theory. In particular, I'll distinguish Euler-Bernoulli beam theory is what you probably think of when you think of classical beam theory. And it comprises those two fundamental assumptions that we previously stated. Plane sections of this beam will remain planar after deformation, and they will remain perpendicular to the deformed neutral axis of the beam. That basically assumes that shear deformations or shear strains internal to the beam are roughly negligible. And what that means is you recover this, plane sections remaining perpendicular to the neutral axis. That's the consequence of assuming that shear deformations are negligible. And that assumption remains valid if you have relatively thin or slender beams. So anytime you have an aspect ratio that's maybe greater than 10 to 1 or maybe 20 to 1, you can reasonably get away with this idealization of the beam through the kinematics of Euler-Bernoulli beam theory. Now, there's an analogous theory that applies to plates, which says similar things, but more specific to how plates deform. So if you consider, let's say, some plate, and in analog to how we described the deformation of beams, a beam you can think of as having a neutral axis or a neutral fiber. It's kind of like a particular elevation through this depth of the beam at which it passes through, let's say, the centroid of the cross section of that particular beam. There's an analogous interpretation of a neutral surface in the case of plates. Sometimes it's called the mid-surface, but it basically constitutes the exact midpoint or mid-plane of a particular plate. And it has an analogous interpretation in plate theory as the neutral fiber or neutral axis has in the case of beam theory. But the fundamental assumptions of plate theory, in direct analog to Euler-Bernoulli beam theory, state that rather than looking at individual cross sections cut through some beam, plate theory instead looks at small material fibers that you might hack out that span the full depth through the plate. So rather than looking at a cross section, look at a single fiber that goes through the full depth of the plate and examine what happens to that fiber before and after deformation. Under the assumptions of plate theory, and in particular Kirchhoff-Love plate theory, this fiber will deform in a fashion which basically means if it was originally straight, it will remain straight after deformation, and it will also maintain an orientation which is perpendicular to the mid-surface of this plate. So if you like, you can kind of think of it in those terms that Euler-Bernoulli beam theory says plane sections remain planar and perpendicular to the deformed neutral axis of a beam. Plate theory says straight fibers remain straight after deformation and perpendicular to the mid-surface of the deformed plate. So very much analogous concepts. And again, here too, that assumption of this fiber through the thickness of the plate, maintaining an orientation strictly normal to the deformed mid-surface of the plate, that assumption arises precisely by assuming that the transverse shear strains through the plate are negligible. Now, we can enforce that analytically, and it applies quite well to relatively thin plates. But not all plates and not all beams are necessarily thin. And in some cases, you might have beams or plates that can't quite fit into exactly these idealizations, where the depth of the beam, maybe it's somewhat slender, but if it becomes sufficiently thick or deep, at a certain point, shear deformations are no longer strictly negligible. And this particular assumption, the assumption that the shear deformations are negligible, goes away. And it's not really appropriate to consider that anymore for relatively thick beams. In those situations, there is an alternative theory of beams. Actually, there are many alternative theories of beam and plate deformations. But one in particular that's one worth looking at is this slightly more generalized description of beam bending and also plate bending as well. Both of them still analogous, but really they maintain this assumption that the cross-section remains planar in the case of beam theory, or that the neutral or one of these fibers through the thickness of a plate remains straight after deformation. So plane sections remain planar, straight fibers remain straight. The thing that we get rid of is the assumption that they remain perpendicular to the neutral axis or to the deformed midsurface of the plate. That's the thing that we say, well, we can't quite neglect shear deformations, so we're going to allow maybe this fiber to deform in a way such that it's not perfectly perpendicular to the deformed mid-surface of the plate, and such that this cross-section isn't perfectly perpendicular to the neutral axis. In the case of beam theory, that set of assumptions is sometimes referred to as Timoshenko beam theory, named after Stephen P. Timoshenko, a very famous civil engineer, also a significant contributor to the theory of elasticity generally. He's highly cited throughout the textbook. You'll notice, there are citations everywhere referring to his book on elasticity. And Reisner-Mindlin plate theory is the analog in the case of plate deformations. So really analogous theories that apply in different situations. And you'll notice if you go and you use these different assumptions in the context of a finite element code, they might say whether a particular beam or plate idealization uses one of these two different notions of beam theory or plate theory, Euler-Bernoulli beam theory or Timoshenko beam theory. And it all boils down to this. Is it neglecting shear deformations or is it including shear deformations? Is it allowing the cross-section to deform relative to the neutral axis, or is it maintaining a perpendicular orientation? So that's really the fundamental distinction. And again, really, if you take away nothing else from today's lecture, what I want you to take away is this, that these theories are really approximations. They're simplifications of the much more general theory of elasticity as we've established it. But it basically means that, all the things that you've done in the past, everything from structural analysis to strength of materials that's predicated on these assumptions is inherently doesn't include all that generality. And again, you lose a lot of the kinematic description of, warping of these cross sections or warping of these fibers under deformation. And that becomes more significant as you have, again, thicker plates, but it also becomes more significant if you have more complicated composite beams or plates. In those situations, if you have multiple materials comprising a beam or comprising a plate that might be layered in different structures, then the kinematics actually become much more complicated, and the resulting distribution of strain and stress through the depth of this beam or plate now can no longer reasonably be idealized through these simplified assumptions of beam or plate theory alone. So just bear those details in mind, that really this is all assumptions. However, it is still extremely useful. There's a reason that all of your prior coursework has been exclusively focused on analyzing these kinds of structures, because applying the more general theory of elasticity to analyze the deformation of beams or plates can be very cumbersome. And coming up with analytical solutions to these problems is anything but trivial. So we like to use these theories because they make our life a lot easier, like a lot easier. You can actually come up with solutions to these problems as opposed to the more general theory of elasticity, which normally requires that you use some kind of finite element program to come up with the solution, particularly for complicated geometries. All right, so that's all interesting, but let's actually dive into what exactly do the kinematics of these assumed forms of deformation look like, both for beams and plates. And we'll continue in our side-by-side parallel analysis of beams and plates, just so that you maintain the connection between how those two things are really, not so distantly, separated. They're quite related. So in the case of a beam, let's take a look at a particular cross-section cut out of this particular beam, and we'll represent its neutral axis as this dashed line. Similarly, in the case of a plate, let's look at a particular fiber that spans the full depth of this plate, pull it out of this plate, and also this dashed small patch or area will be representative of the mid-surface of this plate. All right, so now what we want to do is figure out what exactly happens to this cross-section or this fiber in a plate under various deformations. And if I've said that according to, let's just pick Euler-Bernoulli beam theory, at this stage, it doesn't matter whether we're considering the, Timoshenko beam theory or Euler-Bernoulli beam theory. All we really want to know is if this cross-section is going to remain planar, how can we characterize the displacements of various points oriented on this cross-section before and after deformation? And we'll do the same thing looking at what happens to this straight fiber, which will remain straight, but it might kind of rotate a little bit. All right, so to do that, we have to take a look at exactly what goes on under, let's say, different rotations of this cross-section and different rotations of this fiber through the depth of the beam or through the depth of the plate. Starting with beams. All right, so what happens to this, cross-section after deformation? If we assume that the cross-section remains planar, then it basically says that this cross-section has to just rigidly rotate almost about any of these two out of plane or transverse axes. So this cross-section originally oriented and aligned with the y and z in plane dimensions, I can rotate it about the z-axis, I can rotate it about the y-axis, and it'll give me different orientations of this deformed kind of cross-section. Now, what I want you to take a look at is exactly what happens to individual points oriented on this cross-section under these assumed kind of rigid rotations of the cross-section as a whole. And specifically look at the axial displacement of any point you want to look at on this cross-section. I'll just look at the corner here. Now, in the case of a rigid rotation of the cross-section, let's say about the z-axis, and in particular, just for the sake of visualization, I'll kind of actually treat it as maybe a negative rotation about the z-axis. And the way that I'll define my sign conventions for these rotations is by using our trusty right-hand rule. So if I wanted to represent, let's say, a positive rotation of this cross-section about the z-axis, it would be basically in an opposite orientation to what I'm showing here. A negative rotation about the z-axis would be, by the right-hand rule, in a direction of rotation where my thumb is pointing opposing the z direction. So theta z in this case is actually a negative rotation, but it would give rise to a positive x displacement at this point. All right. Same thing if I were to look at rotations of this cross-section about the y-axis. This time, theta y, the rotation of the cross-section about the y-axis, or the y transverse direction, is interpreted in this case as a positive rotation, giving rise to a positive x displacement at that point. Now, what's interesting is that I can look at any of the points on this cross-section and see how do they depend on the magnitude of this rotation. Certainly, if I look at what's the axial displacement occurring right at this neutral fiber location, it doesn't matter how I rotate this cross-section, the displacement of points right at the neutral fiber axis location is just, it's not going to displace axially at all. It really depends on how far away am I from the neutral axis and exactly, what position do I have on this cross section, which determines, where this point is going to go. Is it going to displace this way? Is it going to displace this way for a given chosen rotation about some transverse axial direction? All right. Now, I can represent that in a few different ways, but the way that I particularly like to represent this is by supposing that if I wanted to compute what is this ux position, I can compute it basically through a cross product. And in particular, it is the cross product of the rotation of the axis, or the rotation of the cross section, represented as a vector. And I can assemble it into a vector of 3 components. But really, if I'm only allowing this cross section to rotate about its transverse axes, in particular about the y or z axes, and I assume that there's no rotation about the x axis, so there's no angle of twist going on, then it's kind of like I can say that there's no rotation about the x axis, but the cross section might rotate about the y or z axes. Now, I also said that really it depends on where in this cross section I'm looking. If I want to know how much does a particular point displace, either in the positive axial direction or the negative axial direction. And it turns out I can relate the position in the plane of this cross-section expressed in terms of the y and z coordinates of this point. And I can relate it to each of these two different rotation components about the out-of-plane axes to come up with this kind of nice representation, again, as a cross product. And it turns out, it's a rather general statement, that this rotation vector taken in cross product with the actual position of this point, measured, assuming that it's basically just a y and z coordinate that I'm looking at, and assuming that the x coordinate I can just neglect or say it's 0, the cross product of this rotation vector with the position vector of some point on this surface gives me precisely the description of that kind of axial displacement. If I were to work out exactly what this cross product looks like, multiplying through these terms, I get an explicit expression for what is the axial displacement of some point at any location on the cross section that varies as a function of both y and z, the transverse coordinates measured relative to the neutral axis of the beam. And it depends, again, on these different rotations about each of the transverse axes of the beam. So interestingly, you'll note that the sign of each of these terms is, not consistent. One has a plus sign, one has a minus sign. And again, it has to do with some of the details of, partially taking this cross product in order to relate how these displacements, the axial displacements, relate to these rotations. But in any case, that's kind of more in the details. All right, so in the case of plates, and looking at the deformation of one of these fibers through the depth of a plate, we can do basically the same thing and apply essentially the same formula to look at how does, let's say, a particular point measured somewhere along the axis of this fiber, how does that point deform in plane relative to the plate? So really, if I'm looking at this particular fiber and I'm saying all it can do is rotate, I can rotate this fiber, again, about the y-axis, I can rotate it about the x-axis, and it'll kind of change orientation appropriately, or it might do both at the same time. If I rotate it about the y-axis, I'll generate a displacement in the x in plane direction. But if I rotate it about the x-axis, I'll generate a displacement in the in-plane y direction. So there's kind of a weird cross-coupling between rotations about x generating displacements in y and rotations about y generating displacements in the x direction. But if I assume that there's no, sometimes they call it drilling rotation, if there's no rotation about this z-axis that's aligned with this fiber, then I can do the same thing as how I did for my beam kinematics. And I can say that there's only two rotations I'm going to allow. Rotation about the x in-plane dimension of the plate and rotation about the y in-plane dimension of the plate, assuming 0 rotation about z. And I can also look at what happens to various points that vary only with z coordinate through the depth of the plate. Taking this cross product, I basically get two expressions, one relating the x displacement to the y rotation, and another which relates the y displacement to the x rotation in this case, both of which vary linearly with the z coordinate through the depth of the plate. All right, so a little bit complicated, a little bit of a departure from what you might be used to thinking of, how these things vary. But really the thing I want you to take away from this is that axial displacement varies linearly with the in-plane dimensions of the cross-section or with the z dimension through the depth of the plate. All right, so that's the main takeaway from kinematics and how we represent things and how we relate assumed rigid deformations of either the cross-section or the fiber to resulting in-plane or axial deformations of beams and plates. Now, what can we do with this? Once we've established this relationship, either the axial displacement in a beam that varies as a function of position on the cross-section, or the in-plane displacement of some kind of point along some kind of vertical fiber orientation that varies as a function of position z. We can also take derivatives of these things. because ultimately, we don't just want displacements. We want to know strain. And in order to compute strain, we have to use our classical strain displacement relationships. And if you remember what those look like, they expressed some relationship between the partial derivatives of the displacement field, its various components, with respect to various position or coordinates of various points and how they varied with respect to those different coordinates. So we might want to look at things like, how does the ux component of displacement vary as a function of y? We can compute its partial derivative. And notice that it's basically just directly equal to theta z, again, assuming that it's a rigid rotation that's happening. And same thing, we can look at partial derivative of ux with respect to z. And notice that it's related to directly just this assumed constant rotation theta y. We can do the same thing. We can look at ux partial z, uy partial z, and notice that it's related to the in-plane rotations, theta y and theta x. And again, we have these signs showing up partially because of how we've set up this, representation of the cross products. Okay, so now that we've come up with these relationships, now we need to actually invoke some of the assumptions of Euler-Bernoulli beam theory in particular. Now, we've said up to this point only that the cross-section remains plane or that the fiber remains straight, but we haven't strictly enforced the requirement that it maintains an orientation that is strictly perpendicular to the neutral axis of the beam, or that the fiber maintains an orientation perfectly perpendicular to the mid-surface of the plate. To enforce those conditions, we basically have to invoke the assumption that the transverse shear strains, either in the beam or through the plate, are roughly negligible or close to zero. And to do that, all we have to do is pull out our normal expressions as we previously derived them through the strain displacement relationships for those particular components of shear strain. The transverse shear strains in a beam, two components, the epsilon xy component and the epsilon xz component, measuring the relative strain, in each of the transverse directions. We can set those as being approximately equal to zero, which is roughly equivalent to saying that this term in this expression has to be equal to this term shifted by a minus sign. Same thing. This term has to be equal to minus uz partial derivative with respect to x. And that's precisely how we come up with these relative approximations that relate various partial derivatives of ux with respect to y to minus uy with respect to x. Similarly, ux with respect to z is roughly equal to minus uz with respect to x. And the situation is very similar in the case of plate theory. Again, the advantage of doing this was to basically note that, we're doing almost the same thing. The only difference here is which particular components of shear strain we actually enforce to be roughly equal to zero. In the case of a plate, it's the epsilon zx and epsilon zy components of strain corresponding to the shear strains through the thickness of the plate. But in the end, what we get is something that looks kind of like this. Once we enforce these conditions, and after we note from our previous kinematic assumptions, basically these, observing that we already know what ux with respect to y is, and ux with respect to z, and x with respect to z in the case of plates, we assumed that they were representable in terms of these rotations. And if we further say that shear deformations are relatively negligible, transverse shear strains in particular are negligible, then we can take this term and basically pass it through this other expression and finally come up with these resulting expressions that say that go back there. There we go. That say that each of these rotations of the section is not defined independently of the deformation happening due to transverse deflection or deformation of the beam. Or analogously, the rotation that occurs of a particular fiber is not an independent kinematic variable that we have to solve for. In fact, it depends directly on the actual deformed orientation of the plate. So really what's important to note here is that these rotations of the cross-section depend on how the transverse deflection varies as a function of axial coordinate. And similarly, the rotation of the fiber about each of these in-plane axes depends on how the transverse deflection of the plate varies as a function of the in-plane coordinates. So it's a little bit of a switcheroo, if you will, but it enables something interesting. It enables us to basically say that if we combine all these expressions together, if we had our expression for what's the axial displacement of some point as a function of these section rotations, and if we related the section rotations to the transverse deflection field of this beam, we could do the same thing for plates. What we find is we can combine all these expressions together and come up with an expression for the axial strain in this beam, basically just the derivative of the axial displacement component with respect to axial position. We can determine that exclusively in terms of partial derivatives, in this case, second partial derivatives of the transverse components of displacement. So somewhat interesting. Similarly, we can come up with expressions for strain in a plate by plugging together, plugging all these different equations into one another and simplifying terms to come up with not just what's the axial strain in this beam. In the case of a plate, we might be interested in looking at the in-plane components of strain, all three of them in this case. So strain in the x direction, strain in the y direction, and shear strain in the plane of the plate. That's really the distinction and where things get interesting and how things start to become more complicated in plate theory as compared to beam theory. Beam theory really assumes that the only quantities of interest that you care about are purely axial strains and axial stresses. In the case of plates, you're looking at in-plane strains and resulting in-plane stresses. That's where things get fun. Okay, but I can derive all these expressions. I can basically say that either the axial strain or the in-plane strains depend on the out-of-plane displacements or the out-of-plane displacements of the plate or this beam. And really the nice thing that we can interpret from all of this is the following. Consider some small segment of a beam. And we'll just kind of like consider just this small section that might be, rotating a little bit. Maybe it also develops a little bit of curvature. If you were to look at what happens to the orientation of this beam, and more specifically, the orientation of its neutral axis. The neutral axis might, incline a little bit, depending on how much this beam has displaced in a direction transverse to the axis. So the transverse displacements are really not axial displacements. Their direction is basically perpendicular to the axis of the beam. So if I'm deflecting this beam transversely, I can look at what is the resulting slope of this beam after it has deflected. And that slope is precisely the derivative of this, transverse displacement field with respect to axial coordinate. So if you like, you can think of this kind of inner angle, roughly approximated as an angle, but really it's the slope. The slope of this beam under deformation is really just the derivative of the y or transverse displacement component with respect to the axial coordinate x. You can do the same thing with plates and suppose that the transverse deflection field, or basically the UZ component of displacement of the plate in the direction transverse to the in-plane dimensions, that too will also give rise to maybe some inclination or rotation of the mid-surface relative to its original orientation. So it might kind of incline in one direction, or it might incline in the other direction. And in addition to that, it might also develop some curvature and look like it's not perfectly flat, but it might actually look a little bit curved like that. Now, the fundamental assumption of Euler-Bernoulli beam theory is that this interior angle and this interior angle have to be the same. Or in other words, that in order to enforce the condition that the plane section remains perpendicular to this fiber, we have to say that really the slope or the rotation of the neutral axis has to be equal to whatever the rotation of this cross section is after deformation. if we were to invoke the more general Timoshenko beam theory, which relaxed that condition and said, well, the beam might orient a little bit this way, but maybe the fiber doesn't want to do that. Maybe it wants to orient the other way. That would be perfectly admissible under Timoshenko beam theory, in which case the rotation of the section would become its own independent kinematic variable that we would have to solve for, independent of the transverse deflection field of the beam. That obviously introduces a lot of complexity, and it's not something that we're going to dive into a lot of detail on, but I just wanted to mention that really this assumption that plane sections remain planar and perpendicular is really a limiting one. It's useful for slender beams, but in some cases you do have to relax it, and this is precisely where it comes into the picture. If you do, however, enforce that these two things are equal, as we previously said, by assuming that shear deformations are negligible, then we can basically just say that those two angles, these two rotations, if you will, are just one and the same. And the same thing applies in the case of plates. Again, the relative inclination angle of the plate would have to be equal to whatever the corresponding rotation of the fiber through the depth of this plate would look like. Otherwise, in the more general case of Reisner-Mindlin plate theory, obviously, the fiber could deform in any arbitrary fashion, regardless of how the plate is necessarily deforming, and you'd have to treat its relative orientation as an independent unknown. But in the case of Kirchhoff-Love plate theory, as in the case of Euler-Bernoulli beam theory, it all just depends on transverse displacement alone, which is really nice because in the end, all we have to do to combine all these things together is by supposing that I can define some intermediate quantities, things that I'll just call curvature. Curvature of this line segment is really proportional to the second partial derivative of the transverse deflection field with respect to the axial coordinate. In the case of beams, that's relatively straightforward and easy enough to interpret. We just take uy, which depends on x, and take its second partial derivative with respect to x. This gives me some kind of description of curvature relative to displacements in the y direction. And I could do that not just for displacement in the y direction, but also displacement in the transverse z direction as well. So really, there's two components of curvature that I would have to look at for a beam. Curvature relative to displacements in the y direction and curvature relative to displacements in the z direction, two transverse directions. In the case of plates, this is where things get weird. I can take second partial derivatives of the transverse deflection field, now uz. I can take second partial derivatives with respect to x, giving me some curvature like you would see on this kind of line segment. I can take its second partial derivative with respect to y, giving me curvature of the plate in that direction. But I can also take sort of a mixed partial derivative, both with respect to x and y. And I'll call this kind of mixed term the kappa xy or kappa yx term. It's sort of a description of the interaction between bending that might happen of this plate relative to changes in x and relative changes in y. And you kind of have to include all these different terms, as you'll see in a minute, in order to actually relate how does the transverse deflection as measured through the curvature of this resulting plate, how does it relate back to the resulting in-plane strains and how they vary through the depth of this plate? Okay. Now, in order to understand that, we can invoke our standard definitions of strain and just say that really axial strain, as I've said previously, is based on our previous derivations. Axial strain in a beam is just the partial derivative of ux with respect to x. We can plug in our expressions for these, basically these kappa or bending curvature terms, these second partial derivatives of the transverse deflection, different components of it with respect to x. And we find that effectively our expression for axial strain will vary as a linear function of these bending curvatures multiplied by depth or relative distance measured relative to the neutral axis of this beam. In the simple case where we're just looking at, let's say, a beam that's bending only due to deflections or transverse deformations in the z direction. In this case, we can look at some neutral axis of this beam, and before and after deformation, assuming that this beam is only undergoing bending deformations, we can reasonably assume that this neutral fiber is not undergoing any kind of axial extension or compression. That's fundamentally an assumption of beam theory as well, and it applies really only to straight beams. There are situations where if you had an initially curved beam and you tried to deform that beam, now some of those assumptions fly out the window. But if you have a perfectly straight beam to begin with, and if you assume relatively small bending deformations take place, then it's reasonable to assume that this neutral axis maintains its same length. But if you look at any other kind of fibers above or below the neutral axis of this beam, in particular, if you look above the neutral axis, you'll notice that this fiber, which might have had some initial length delta x, is now going to shrink a little bit. Fibers below the neutral axis will elongate a little bit. And that variation, due to bending curvature, which is nominally how curved is this line segment, that's kind of what these bending curvature terms are really representing. We can see that it varies linearly as a function of z measured relative to the neutral axis. If I go up and take a positive value of z and plug it in here, if I have a positive value of bending curvature corresponding to kind of a happy smiling face in terms of how the beam is deflecting, that's kind of our positive sign convention for bending curvature. So if kappa z is positive as shown here, and if I'm looking at position z above the neutral axis, then really what it says is I should have a resulting axial strain that is negative, indicating that fibers above the neutral axis are being compressed. Conversely, if I look at values of z below the neutral axis, negative values of z, then obviously I'll get, positive values of strain indicating that it's elongated. A similar principle applies in the case of plates. The only difference here is that basically it's not just that we're looking at axial strain. As I mentioned, we have to look at all the different in-plane components of strain that might develop in a plate. And it might vary also as a function of depth through the plate. That's the interesting observation here and the connection with beam theory, is that strain also varies as a linear function of depth through the beam, or rather, all through the plate. It applies both to plates and it also applies to beams. But the idea here is that if I look above, let's say, the mid-surface of this plate, an analog to the conception of how neutral fibers in this beam maintained initially just the same length before and after deformation, the same applies to the mid-surface of the plate. It undergoes basically no in-plane deformations. So the strain in the x, strain in the y, and shear strain of this mid-surface are all assumed to be zero. But if I look above the mid-surface, now I might start to develop different components of strain. I might have epsilon xx strain, so it might be contracting in this direction. I might have epsilon yy strain, it might be contracting in that direction, and it might also be shearing. And it turns out that there's a direct correspondence between each of those different mixed terms of curvature, represented as different partial derivatives of the transverse deflection with respect to x, y, or x and y. And I notice that really these different components of strain, in-plane strain, just vary each linearly with respect to depth z. Kind of cool. So if I were to take a particular top-down or bird's eye view of what's happening to a particular slice through this plate, maybe somewhere above the neutral axis, what I'd see from this bird's eye top-down perspective is that this slice of material might be undergoing some combination of those different modes of strain, in-plane strain, and they will vary as a function of depth through the plate. So all these things you can put together, and you can relate all these things together in a very nice and concise kinematic relationship. So really what we've established through the assumptions of Euler-Bernoulli beam theory, and by extension to plates, this kind of assumption that basically we can relate transverse deflections as measured through bending curvature to in-plane strains or axial strains in a beam, and how they vary as a function of position on a cross-section or as a function of depth through the plate. Now, I think that's probably all we have time for today. We'll pick up on more of our discussion and continue our comparisons between beams and plates, but I wanted to reserve time just to be able to pass back the midterms. So with that, I'll go ahead and stop. Here we go.